Now we will see. Now what we will see is that that is nothing but the lag error and its adjustment in energy meter. Lag error and its adjustment in energy meter. So basically what is this lag error means? Lag error means it is because of the resistance of shunt coil, that is the angle between VL and phi sh, it will not be equal to 90 degrees, else it will be equal to how much delta, which is not equal to 90 degrees. This thing we have already seen in that deflecting torque equation of that energy meter. So basically when you see this this energy meter circuit diagram, you can see here this is nothing but that pressure coil. This is nothing but that pressure coil or the shunt coil, and this is nothing but that series coil. This pressure coil or shunt coil is connected parallel to the supply or that load. It is connected parallel to that load. So this pressure coil or shunt coil is going to have a resistance Rp, and also it is also going to have a reactance Xp. Now when you take this equivalent circuit of this pressure coil or shunt coil, how it looks like means now how it looks like means that from equivalent circuit of that energy meter, how it looks like means that whatever that pressure coil is there, no, or shunt coil, it is going to have some resistance and it is going to have some reactance. Okay, this is jxp and this is nothing but rp, and in that pressure coil we are going to have some current ip, and the voltage across this shunt coil will be vl because it is connected across load. Same voltage is applied, same voltage is applied. And also one thing we have to observe is that why this ip will be sinusoidal, because whatever that voltage this we are connected to that energy meter is there, no, this is an sinusoidal voltage. So it is expected that the current is also an sinusoidal current. ip is also an sinusoidal current. Because of sinusoidal voltage we are getting sinusoidal current. It is expected that under steady state condition. What does steady state means? Steady state means all the currents and voltages are sinusoids. That is the thing. And now because of this ip, this shunt coil is going to produce a flux phi sh. This shunt coil is going to produce a flux, what to say, this has an phi sh. Okay, it is producing an flux phi sh. Now since this is an RL circuit, it is an RL circuit, then the angle between this voltage phasor and current phasor, it will not be 90 degrees. Okay, rather it will be less than 90 degrees, and current lags this this current lags this voltage VL. Okay, and we already know that phi sh bar and that ip bar are in phase. Okay, are in phase because what means, because ip created phi sh, ip created phi sh, that's why current creates flux. And also one thing, another thing we have to assume is nothing but whatever this load is there, no, the load we are connected, no, that is an pure inductive load, no, not pure inductive load, it is an inductive load, such that the phase angle between these two IL and VL is nothing but phi. That is a lagging power factor load of cos phi is connected to the energy meter. Okay, that is one thing we have to observe. Okay, that is one thing we have to observe. Okay, that is VL and IL, that angle will be equal to phi. So that is a lagging load is connected to that energy meter. Now drawing the phasor diagram for this thing, how it will be looking. So we are going to have this supply voltage, that load voltage VL, and lagging in this thing we are going to have that load current. This is an phi. Now the angle between this VL and IP, it will be less than 90 degrees. That is, it is an, what to say, it is an, say this angle to be an delta. Okay, we already seen that delta is equal to tan inverse of that XP divided by RP, because if it is an RL circuit. For an RLC circuit, that power factor angle will be this equation, already known from the circuits. This is that thing. And also we know that whatever that series flux produced, that series magnet is going to produce flux, no, that flux will be proportional to that this current, because both are in series, load and that series magnet coil are in series. Okay, and VL will be proportional to VL, that phi sh will be proportional to load voltage, because VL created IP and IP created phi sh, like that. Okay, and the angle between this or we can see, no, will be proportional, but that flux will be there, no, it will be in phase in that IP, because current created flux, that is the thing. Okay, it will be proportional here only, proportional, but in phase. Okay, now the angle between this phi SC bar and phi SH bar will be delta minus phi. Okay, this is nothing but that thing, that a phasor diagram. This is how we got. Now then with these equations we already know that torque equation is given by TD, that the TD net average value, which will be equal to, or which will be proportional to phi SH RMS into phi SC RMS into sine of angle between these phi beta, no, sine beta. Here beta is nothing but delta minus phi. Already we have seen this equation. And here that alpha is equal to 0. Assume that alpha is equal to 0. Then cos alpha will be 1. Okay, that is the thing. This is a non-ideal case. This is an non-ideal case. Okay, now say this TD as an TD dash, say will be proportional to VL bar, because it will be proportional both, already we have seen. And phi SCR will be produced to IL bar, because IL only created phi SM now. So this will be sine of delta minus phi. Okay, that is the thing. Now if it is an ideal case, so for an ideal case, that is, this is for an ideal case. Okay, ideal case, that RP is equal to 0. If RP is equal to 0, then TD will be proportional to VL IL cos phi. because if rp is equal to 0, then delta whatever that tan inverse of xp by rp is there, no? If rp is equal to 0, then this delta will be 90 degrees. So sine 90 minus 5, whatever the sine 90 minus 5, you'll getting as an cos 5. Okay, then what we will get, then that angle between phi sh and VL bar we are going to get as a 90 degrees. And also this is the thing, now we will draw that phasor diagram in ideal case. Now in ideal case the phasor diagram will be, this is VL bar and we are going to have that IL bar. It is nothing but that phi, and we are going to have that phi, this is an IP and this is an phi sh and 90 degrees lagging, and the angle between these two things will be 90 minus 5, and here it will be proportional to phi sc. Okay, both are in phase because current and all these things. Okay, and ideal case also we see. Now error in deflecting torque. Error in a deflection torque will be equal to that TD dash minus TD divided by TD. Okay, now what we are going to get is nothing but this VL bar IL bar sine of delta minus phi minus VL bar this IL bar magnitudes, RMS values both are, cos phi divided by what to say, this VL bar IL bar into cos phi. Now what will get this error, sine of delta minus phi divided by cos phi divided by cos phi. This is the error. This is the error in deflecting torque, what we are going to get. And also another thing, we have previously got it as an, moreover, revolutions made by the disk will be equal to k times of integral VL bar and IL bar, okay, sine of delta minus phi into dt, which will be not equal to k times of energy. This is not an ideal energy consumed by that load. Okay, this is why it is happening, because rp is not equal to 0, shunt coil resistance. Now if rp is equal to 0, then delta will be 90 degrees, then number of revolutions will be equal to k times of integral VL bar IL bar, and the sine of this will be 90 now, delta, so it will be cos phi into dt. So this will be equal to k into this part is nothing but energy consumed by that load, load. Okay, energy consumed by that load. Okay, so this is that thing. Okay, now this is nothing but that energy consumed by that load. That is, for an ideal case, what we can say that the number of revolutions made by the disk will be proportional to energy consumed by that load, because here all the parameters are load voltage, load current and load power factor. That is the thing. So energy, because this is an power equation, active power equation, and there is an time. So energy is nothing but a product of power and time. So what this is, these are the two errors we are going to get when whatever that pressure coil resistance is there, no, because of that pressure coil resistance we are going to get this error in that deflecting torque. And also if that pressure coil resistance is not 0, then we are not getting that revolutions are not proportional or not equal to that energy consumed by that load, not equal to that energy consumed by that load. That is, we are going to get error in the number of revolutions made by the disk, and also we are going to get the error in the deflecting torque. Now what we should is that, now what is that lag adjustment? So now we will see about that lag adjustment. Lag adjustment. Lag adjustment means simple thing, making that delta is equal to 90 degrees. That is the angle between VL bar and IL bar is equal to VL bar and phi SH bar 90 degrees. Making delta is equal to 90 degrees called as lag adjustment. Making that delta is equal to 90 degrees is called as an lag adjustment. Okay, this lag adjustment is done by using shading coil or shading band on central limb of shunt magnet. Central limb of that shunt magnet. Okay, and this shading coil must be an highly resistive. Highly resistive. Then only delta will be equal to 90 degrees. Delta will be equal to 90 degrees. And how this process is done, it is of not necessary. Just remember this thing. This is enough. So that is we are going to have that central limb of that that shunt magnet is there, no, and we are going to have that shunt coil here like this, and on this thing we are going to put an shading band like this, shading copper band. It is an highly resistive, and this is going to make that delta is equal to 90 degrees. So when delta is equal to 90 degrees, what the two cases we have got now? When delta is equal to 90 degrees, the revolutions made by the disk will be proportional, will be equal to the k times of that energy consumed in the k times that of energy consumed in the load. We are going to that thing. Ideal case we are going to get. That is what we necessary. This is done by using that shading band. Okay, and another thing that we are going to get that deflecting torque will be directly proportional to power. This is the load power for ideal case. Load power. If RP is equal to 0, that is nothing but delta is nothing but 90 degrees. So these two things will happen if you by using that shading band. By using this shading band, and how it is done, it is not necessary. This is what. Okay, this is what. So lag error means, what is a lag error? Because of that resistance of that shunt coil, the angle between this thing delta will be not equal to 90 degrees, and this error is removed by using that shading band. And this is about that lag adjustment. Thank you.